So the today's topic is first part, our introduction of spring. Now, first is definition. It is defined as elastic body whose function is to deflect or deform by storing the energy when loaded and recover its original shape when load is removed. Very very simple definition. So spring is used to deflect or deform by storing and when loaded and recover its original shape when load is removed. So as far as applications are concerned, the definition of spring is very clear if you understand the application. What is the first application? To measure the force. You know that in our day-to-day application, spring balance is there. So in the spring balance, how much amount of load is applied over that compression spring and how much is the compression of the spring, it is directly proportional to the force apply. So we can measure, we can calibrate our load with spring compression. So that is my first application. So to measure the force, spring balance is used. To absorb the shock and vibration, you know that in our day-to-day life we are using two-wheeler and four-wheeler. In that, shock absorbers are used to absorb the shock. In that, obviously spring, which is going to store the energy, which is generated through our shocks. So that is one more aspect. To apply the force, so in our clutches, brakes, valves, we need to apply some force. So that can be generated by using spring. So to apply the force, also one of the application. Next is to store the energy. We know that in our nowadays electronic clocks are there, but in the previous days clocks are work by using stored energy by the spring. Or you might have seen old mechanical toys. In that there is a key. By storing the energy using that key, we can run that toy. So that is also one of the application to store the energy. So if you understand these four applications and its functions, definitely you will get 4 marks in our exam. So this is basic question which is maximum time asked in our exam. So what are the application of spring? You just write the main application and its function. Next is classification. How the spring is get classified. So if you just read that our screen, you'll find that there is a helical spring, conical spring, torsional spring, disc or bellows spring, leaf spring. One by one we'll see in detail. Now you'll find in front of you on the screen, you'll find, just wait here, Sheikh Siraj has raised his hand. You can unmute Sheikh Siraj. Are you having any doubt? Okay, let it be. Now, here in the classification, you can find different kinds of spring on the screen. Classification, helical spring. The helical spring is having basically two types: helical compression spring and helical tension spring. Where you can find these kinds of spring? If you just see, take an example of our bicycle. Suppose bicycle, you'll find that in our bicycle there are different kinds of springs. You can find spring in our bicycle stand. You can find springs in our bicycle seat. You can find springs in our bicycle brake system. So simple helical compression spring you can find in our ball pen also. There is a button type ball pen. In that you'll find a spring, helical compression spring inside that pen. If you just see helical tension spring, the helical tension spring also you can find in our simple bicycle stand. So If single side bicycle stand or double side bicycle stand is there, then you will find there helical tension spring is there. Now if you just see the conical spring, you can find this conical spring in our bicycle below the bicycle seat, or you can find it in our shock absorber of a two wheeler or four wheeler. So conical spring is there. If you just observe our spring system, brake system in our bicycle, there is a torsional spring. There is a torsional spring which is used in our bicycle brake system. So this is torsional spring. Torsional spring is having a twist which has to be created to store the energy. So these are helical spring, conical spring, and torsional spring. In addition to this, you can have a disc or bellows springs. So disc or bellows spring also one of the spring that is generally used in our suspension system. Leaf spring is also used in our truck suspension system. The bellows spring is also available in our some of the clutches. Okay, so these are the different types of spring. In all these different classification, you'll find that storing of energy is must in each and every type of spring. So after the classification of spring, let us go for next topic. What are the different terminologies for the springs? Now first, before going to have the terminology, let us look at the picture. You'll find that there is one simple our helical spring, and there is a W load is applied on that. Because of the W load, it get compressed. So how much it get compressed? There is no gap between two coils. It is completely compressed. If such type of spring is completely compressed, then there is a one terminology that can be clear, which is called as a solid length of the spring. ठीक है? Solid length means what? Solid length क्या है? So let us simple word we can explain this. When the compression spring is get compressed until the coils come in contact with each other, then the spring is said to be solid. The solid length of the spring is the, how we can find the solid length? So it is very very simple. You have to count number of turns or number of coils and oh, diameter of one coil. So it is mathematically you can see at the below the figure, mathematically ls, it is indicated by ls, which is equal to n dash into d, where n dash is total number of coils or turn, and d is the wire diameter in mm. So solid length we can find very easily if I know number of coils multiply by wire diameter. So that is called as solid length. So this is first terminology which is used in our spring. So this type of terminologies are asked in our exam for each terminology for 2 marks. So if I know solid length, and if you write this what is solid length, and if you just go for a mathematical equation, you will get definitely 2 marks. So after the solid length, the second terminology which is in front of you is the free length. So what is free length? Now remove the load. You can look at the picture. In that picture, you'll find that there is no load on the spring. If there is no load on the spring, it is in the free condition. When it is in the free condition, then the free length of the compression spring is the length of the spring in the free or unloaded condition. It is equal to, now solid length is very very simple, but the free length is equal to solid length plus maximum compression plus clearance between adjacent coils. Okay, so mathematically, free length, how we can find the solid length plus the maximum compression that can be possible, because the maximum compression, if there is a maximum compression, it get converted into solid length. So maximum compression is released here. So that maximum compression plus clearance between adjacent coils. So adjacent coil means what? Here at the end, you'll find some half coils. So the clearance between that two adjacent coil has to be considered when there is a free lane. Okay. So the free lane that can be n dash into d, which is solid length. Delta max is generally considered for the compression, maximum compression, and there is a clearance. So we generally consider 15% clearance. So 0.15 times d max. So delta max is the maximum compression. So you have to add that 0.15. So total maximum compression plus clearance can be 1.15 delta max. So that is added in the solid lane so that you will get free lane. So free lane can be solid lane plus whatever maximum compression and clearance between adjacent coil. So the clearance which is left in the adjacent coil is here we consider as a 0.15 times maximum deflection. Okay, maximum compression. Now after this free length, the next terminology which is important here is the spring index. So we know that here there are two diameters. One is diameter of the spring, another is the diameter of coil or diameter of wire. Okay. So the spring index is defined as the ratio of mean diameter of the coil to the diameter of the wire. So if I consider capital D as a mean diameter of the spring and small d as a wire diameter, that is very clear if you just look at the picture. In the picture you will find that there is a capital D. Capital D is the spring diameter, mean spring diameter. Okay, and small d is the diameter of wire. So spring index is the ratio of capital D to small d. So spring index is very important when we go for our design of spring calculations. So spring index ratio is used there. So that's why terminology comes here. The terminology is very simple. Spring index is the ratio of mean diameter to the wire diameter. Okay. Next to that, the next terminology is the spring rate, or we can say that it is the stiffness or spring constant K. The spring rate is defined as the load required per unit deflection of the spring. So if there is a unit deflection 1 mm, 1 centimeter, 1, so that means unit deflection, for the unit deflection how much amount of load is required. So obviously it is a ratio of axial force divided by deflection of the spring. So it is denoted by K. The spring rate or the spring stiffness K is equal to force divided by deflection. So force is in generally in Newton and deflection is in mm. So Newton per mm is the spring rate. So spring rate is different for different spring. If you change the spring, obviously the spring rate is going to change. The spring rate is very unique quantity which is important in our spring. Okay. Now the next terminology is the pitch. Just again look at the figure. You'll find that there is a pitch. So what is that pitch? The pitch of the coil is defined as axial distance between adjacent coil in uncompressed state. That means in the free condition, the distance, axial distance between adjacent coils. You can consider any reference point, same reference point between that two adjacent coil, then that is called as a pitch. So how we can find the pitch? Pitch we can find by very simple way. We know the free length divided by whatever number of coils minus 1. So that will be the pitch of the of that spring, or we can have one more equation. So that equation is free length minus solid length divided by number of coils plus coil plus wire diameter. So that is also uh, pitch. So if you take a total free length and if you subtract solid length, so the remaining will be the deflected distance. Deflected distance we can divide it by number of turns. So one uh, deflected distance between one coil that comes from that plus d. So that is also the pitch. So we can find pitch by using this simple equations. So in our stress calculation, spring rate is very important for us. So these are the terminologies. These terminologies is definitely asked for two marks each. So if the two terminologies are asked, then the question is for 4 marks. If the three or four terminologies are asked in our exam, so obviously the question is for 6 or 8 marks. Next to that, here, which type of material is suitable for the spring? So that is one more question that can be raised. So if you just take any simple wire of mild steel and if you try to make a spring out of that, so it cannot store any energy store नहीं कर पाएगा. ठीक है. So what are the desirable properties? So it should have high resilience. High resilience. What is meant by resilience? So resilience means it is the ability of material to store the energy. It is the ability of material to store strain energy. So that is called as a resilience property. So it should have ductility. The material should be ductile. So it can be drawn into wires. It should have high static strength so that whatever load is there, it can be sustained by the spring. It should have high fatigue strength. Fatigue strength, why it is important? Because the spring is generally subjected to repeated type of loading. Because of the repeated type of loading, the spring get fatigue. So it should have high fatigue strength. The creep. So creep resistance is also very important. There should not be any long or permanent deformation due to the loading and temperature. Otherwise, the spring is not it is not reused or it cannot come to its original shape and size. So that's why creep is also important. The next is non-corrosion. There should not be corrosion. If there is a corrosion, then the spring cannot be used properly. So based on desirable properties, the material for the spring can be selected. So the list of different materials in front of you. So as resilience properties has to be stored, we need to cold drawn or harden the spring. Very important. Here you can say cold drawn plain carbon steel containing 0.5 to 0.6 to 0.7% carbon. So 0.6 to 0.7% carbon is added in our plain carbon steel, but it should be cold drawn. Or if you just take a second material, then oil hardened and tempered plain carbon steel. So we need to incorporate such type of manufacturing processes on the plain carbon steel so that the resilience property to store the property or the stiffness to store the energy property can be there. Oil hardened and tempered alloy steel. So hardening and tempering is required. So you can have a material as a stainless steel, or you can have a other materials like phosphorus, bronze, silicon, brass, beryllium, copper, nickel alloy. So our simple copper is not useful. It need to be have a spring copper or spring brass or silicon bronze or nickel alloy. All these are the different non-ferrous materials are also used for the spring. Not a simple metals. There are spring which can be used and which can be manufactured by our non-metals. Like you can find a simple plastic spring also in toys or in our simple day-to-day application. You can find such type of springs also. Okay, so these are the various materials used for the springs. Next thing is, we know that there are very simple arrangement of spring for stiffness and deflection. So the two conditions, the springs are in parallel and the springs are in series. These two conditions are everywhere in our day-to-day life. You can find such type of two springs are in parallel in case of our two-wheeler suspension system. So what is the effect of stiffness, and what is the relationship between the stiffness of springs when these arrangements are provided? So that's why arrangement of spring for stiffness and deflection, these equations that we are going to study here. So springs in parallel. So if you just look at the picture, you will find that there are two springs, spring 1 which is having k1 as a stiffness, and spring 2 which is having k2 as a stiffness, and the force is applied on that. As the force is applied on that, obviously the force is divided between two springs. So force F is equal to F1, which is the force on spring 1, and F2, which is the force on spring 2. And we know that the stiffness, force and deflection relationship. This, just now we have seen the stiffness is equal to force divided by deflection. So that's why force is equal to stiffness multiplied by deflection. So if you just put that here, instead of F, we can say K into delta is equal to K1 plus delta 1 plus K2 plus delta 2. Here, when we pull that complete spring, we say that whatever deflection comes out, the deflection is same. If the springs are in parallel means it has to come down parallelly. So delta is equal to delta 1, which is also equal to delta 2. That means here that delta 1 and delta 2 it get cancelled, and simply we can say that when the springs are in parallel, it may be 1 2 3 4 n number of springs which are parallel. The stiffness of equivalent spring k, the stiffness of equivalent spring k is equal to summation of stiffness of all the springs. So k is equal to k1 plus k2. If there are n number of spring, then we can add together to have a equivalent spring. So if I want to increase the stiffness, you can have a parallel springs. If you add on number of spring, obviously the stiffness is going to increase. So this is one arrangement. Another arrangement that can be the arrangement of spring in series. Okay, so just look at that again picture. You'll find that there is a spring 1 and spring 2. Spring 1 is having K1 as a stiffness, spring 2 is having K2 as a stiffness, and there is a force F. Now, as the force is applied, and it is axial force, so whatever force apply F, it is common for both. So F is equal to F1 is equal to F2, and whatever deflection which comes out, but that deflection is equal to delta is equal to whatever deflection of first plus whatever deflection of second. So the equation becomes delta is equal to delta 1 plus delta 2. Now here also we can put that deflection delta is equal to force divided by stiffness. Force divided by stiffness. So delta is equal to force divided by stiffness equal to F1 by K1 plus F2 by K2. Delta 1, instead of delta 1 we can put F1 force divided by stiffness, F2 force divided by stiffness K2. Now here force is same. So that's why when the springs are in series, the reciprocal of stiffness of equivalent spring 1 by K is equal to reciprocal of stiffness of connected spring. So in this case, you can see that the stiffness is going to reciprocate. So 1 by K is equal to 1 by K1 plus 1 by K2 plus 1 by, and so on up to n number of springs if they are in series. So this is all about the basic fundamental thing. that we must know about the spring. So in the next topic, we'll see about the design equation stresses which are going to apply on this spring.